Alrighty, so I'm going to skip the derivative steps to make this a little quicker. Um, so last time we used the first derivative to find out where you're increasing and decreasing. And then that gave insights to where the max or minimum was, right? So same thing. Um, so we're going to do the same thing with the second derivative, but that tells us something different. So the original function gives you locations on a graph or position. First derivative gives you rates of change. Second derivative tells you about concavity, whether it's opening down in that area or opening down at that critical point, or in general, that section. Okay. All right. So first example, given f of x equal to, let's do something simple. And I'll be sure to upload the videos from today and last time real soon. So given this guy, determine So determine the intervals when f of x is concave up or concave down. So basically you find the critical numbers like we did last time, but um, you test for concavity instead of whether it's increasing or decreasing. Okay. For this one, it's not that interesting, but we're gonna go through the motions. So step one, do an easy one first to refresh you from last time. Find the critical numbers. What was the first step, right? And we did that by finding the derivative, which is this, and then we set that derivative equal to 0. So I'm just going to go ahead and go to this step and solve for x. Okay. Do you have any issues with this? I mean, I can always go back. I'm skipping the intermediate step, but if you want to know, let me know. That okay? Assume you're good then. So my hand's messed up, so. Step two, we're going to need the second derivative. So find f double prime. So double prime would simply be okay. So if your second derivative is positive, then at a specific location, if your second derivative is positive at a specific x value, right? Then it is concave upward. Okay, so I'll draw you a picture in a moment. But notice on this one, do you agree that no matter what x I choose, it's always positive? Right? It's always two, right? No matter what. It's not a trick question.
Yeah.
So since it's always two no matter what, then it's always concave up. What kind of graph is this?
Quadratic.
So it looks like it's a U, right? Parabola.
Yeah.
So do you agree that no matter what you do, it's always opening upward? It is always concave up, right?
Right.
So it makes sense for this to be equal to 2, doesn't it? You'll understand what I mean by concavity.
Like a mirror.
Yeah, I mean that does come up with yeah, certain types of reflections, convex or concave. Let me show you real quick. So if the book says concave up, it means it's just opening upward. Do you agree that no matter it's always opening up, right? It doesn't like suddenly open down, right?
Right.
So it makes sense that the second derivative is always two no matter what, because it's always opening up. So it should be positive for all x. Now, if it was a more interesting function, you'd have it going up and down. So then you'd have a change in concavity, which we'll do in the next example. But is the basic idea making sense?
Yeah.
Okay, so let's put that in English. Since the second derivative is always positive for any x, then it is concave up for all x. So basically, positive, positive, we have happy face. Now, if you get a plus sign, if you get a negative sign on the second derivative, you get concave down. Easy way to remember, right? If your second derivative is negative, then you have concave down. So somewhere on the graph where you actually chose, somewhere on the graph would be concave down if you got a negative value. You got positive, then it's opening up wherever whatever x you chose, it would be concave up. Is that clear?
Yeah.
So to answer the question, I wouldn't answer it. Where is it concave up? What interval?
Between any 2 points.
Yeah, any point whatsoever, right? Or any point x. So for all points. So let's do something that's more difficult. That way it's a little more interesting and you can kind of process some of these ideas. In this next example, we're going to have opening up a section where it opens up and then another section where it opens down. But any questions on the basics for example one?
The concavity is only a single, like a single point on f of x. The concavity is the f prime of x of that point.
Yeah, so basically like if you look at that parabola earlier, right? Let me show you. So if I were to choose this specific x right here, 1.797, and I plugged it into the second derivative, it's going to be 2 no matter what, but I plugged it in, I got my 2. That means I'm concave up at that point. Pick another one, I'm still concave up. No matter what I choose, it's always concave up, so it's not interesting. But if the function, let's say, I don't know, did this, so now I'm concave down from here to here, and then suddenly I'm concave up. See what I mean? So that's where we're going with this. So
What
these,
does the 4 or the 2 mean? Like, is a concavity of 2, what does that represent?
So that the derivative happened to be a constant function of 2. So that means that no matter what x I choose, right? If I were to plug in f of 10 into the second derivative, it's still going to be 2 because it's always 2, right? It's a constant. So that means I'm concave up because this is positive. But let's say if it was a more interesting question, like this was 2x, then I would plug in the number and get 20. Then this would tell me that at 10, I'm positive, therefore concave up. But since I don't have an x, it's always concave up. I think that'll make more sense in the next example, because this one's too basic that really can't do much with it. But I just want to make sure you first understand the basic idea. If the second derivative is positive for x that you choose, that means it's concave up at that location. If it's less than 0, then it's concave down at that location. Oh, excuse me. All right, let's do the next one. Where is it? Here's the one. Determine the intervals for concave down and concave up. Some books use convex and concave, but I want to keep it simple. This book uses, I think, just concave. It doesn't matter. Step 1, find the critical numbers. First derivative will be this. Set that to 0. Solve for x. Well, I didn't ask for max or mins. So let's not worry about that. Let's just find the second derivative. First is right there. Second is here. Okay. Step 2. Find your inflection points. By setting the second derivative equal to 0. So inflection point. What is an inflection point? That's basically whenever you go from concave up to down or concave down to up. Just depends. So a change in concavity is an inflection point. An inflection point could also be a critical number. Most of the time it is. Usually both. But you determine if it's inflection by setting the second derivative equal to 0 and solving for x. So we have an inflection point at 1. So remember they said find the interval when you're concave up and concave down. So we know that it changes after 1. So before and after, it'll be 2 different types of concavity. to just figure it out. So let's choose some test points. I'm going to choose the easy one. 0 and I guess 2. And find out. So we'll do step 3 here. Test points around the inflection point. So plug in 0, your test point, into the second derivative and see if it's positive or negative. So we are positive here, right? I need to make more space. Damn. Okay. That is not the inflection point. Sorry, guys. Start this again. There we go. So we found this point to be positive, therefore it opens up. Second derivative is most likely is negative at 2. So negative 6 times 2 plus 6 is negative 12 plus 6, negative 6, right? Negative, negative, concave down. Okay. So we are concave up from negative infinity all the way until we get to our change of inflection. Concave down from 1 to infinity. Any questions on this example? Do you see how we found the intervals?
So you found the inflection point and then you tested 2 points either side of the inflection point and determined the concavity
Yeah,
intervals.
because
Okay.
that's when it changes. So if you find out what it is before, then we should know at the whole time before that it's going to be the same. Then after the change, it's going to be that right after. But we verified here. I'm going to graph it so you can see it. You can always get the answer with graphing it. But that's not the point. The point is to use your derivatives, do the hard work.
Does this work for like trigonometric functions?
Yeah, it'll work for any function. Any function that you can take derivatives of. Okay. So notice, right? We don't need the max and mins, but what was the inflection point? One? Right here. 1, 6. Oops. 6. No, 7. Okay, so here's my inflection point. So notice that we're concave up before this point, -infinity all the way until we get to 1. Then after 1, we're always concave down. So that's how I got. That's what we're doing. We're finding out when it's pointing upward or downward by using derivatives.
Is the inflection point, if you were to graph the second derivative, is the inflection point where that line crosses the x-axis?
Yeah, it'll be the derivative would be 0. Second derivative would be 0 there. So yeah, it would be touching the x-axis. You graphed it at 1, but on the other graph. Okay. So we use the second derivative to find the intervals of concavity. Now let's use the second derivative to find maximums and minimums, because that's what most people care about. What's my maximum profit? What's my minimum cost, etc. Right? Do one last one and we'll call it a night. I see a good one here. So in this next example, we're going to find the actual extrema values, the max and min. Here's the function, x to the fourth minus 4x cubed plus 7. So step one, you have to find your critical numbers like we did before. Okay, so here it is. And the 4 down, subtract 1, 3 down. Okay. So set this to 0. That's the process, right? Factor out the 4x squared. That'll give us x minus 3. So x is 0, x is 3. So there's my two critical numbers. Step 2, let's find the second derivative. So just do one more derivative. This one. That would be 12x squared minus 24x, right? So what you're gonna do is plug in the extrema numbers into here, and then you'll know if it's opening up or down, which means max or min, right? Min or max. So plugging the critical numbers into f double prime. So far you guys still with me, right? Find your critical numbers, find the second derivative, plug those numbers into the second derivative, and then you can answer the question. So f double prime of, what's the critical number? 0, right? So that will be 12 times 0 minus 24 times 0, which is equal to 0. That doesn't tell me anything other than this is an extrema, sorry, a change in inflection. Okay, so it's not min or max. So let's plug in 3. Again, 3. So that will be 12 times 3 minus 24 times 3. So 9 times 12 minus 24 times 3. Is that 36? I don't know. It's positive though, right? For sure. So since this is positive, we're concave up at 3. We're concave up. So what does that mean? Minimum or maximum?
Minimum?
Yeah, minimum, right? Because opening up. So we have the minimum, which is what they wanted to know, at 3 comma something. I need to find that something. Plug in 3 into the original. Use your calculator or whatever. You should get something.
Negative 20.
Yeah, that's right. So at 3 negative 20, we have a minimum. So just for one more time from the top, find your critical numbers. And we talked about that last time. You got to use the first derivative, set it to 0, solve for x. We got 2 critical numbers. One of them turned out to be a inflection point. The other one was concave up, therefore it is a minimum. And if we graph it, we can see all this nonsense. So we found a inflection point right at 0, 7. Can y'all see the graph or no?
No.
All right, hold on. The inflection point right there, right? 0.7. Now we have the minimum at 3, -20. So we kind of already knew the answers. Let me shrink this down. Oops. Inflection point at 0.7, minimum at 3, -20, or local minimum. In this case, it's global minimum, but do you see what we're doing here? The goal is. Any questions on the 4.4? No, I guess. We take roll and we'll stop here, I guess.